They run like movies. That's very silent. Okay, so sorry to keep you folks waiting. I have another class that I have to come to immediately after this, and there's presentations today and that. So apologies. Okay, so within today's lecture, we're going to be building on our discussions from last time and probably finishing up today our coverage of system dynamics modeling, and particularly of nonlinear models. This is going to be a topic we'll return to a little bit in coming lectures, and it's also a topic where I'm going to try to introduce some elements that will end up being useful in the next component of the class here. So I'm going to be going and taking a look at this model that I challenged you to build between last time and this time, a model which involved two features that were not present in the original model we were working with last time. So it's a model of an infectious disease in a nonlinear context. So we have this context where, in some sense, the whole is greater than the sum of the parts. The people are interacting in the system, and it leads to emergent behavior in the form of an outbreak, for example, which is different than you might expect from the behavior of any one person in this population. So we're going to be adding atop that model today, or looking at the consequences of adding atop. Now, can anyone remind the class, what were the components that I challenged you to add to this model? First of all, I said put it into AnyLogic. I think that was sort of a first step. And then what were the components?
First test and vaccination.
Okay, good. First test and vaccination. And as I think I described it, I suggested putting in place births and deaths such that the population remained in balance. What do I mean by imbalance? Anyone? Yeah. So the number of people getting born is the same number of people dying over time. Overall, the birth and death rates are the same. And what that will mean is we don't have to worry about the effects for this particular simulation of a rapidly growing population or a population that's becoming ever smaller. We'll be dealing with a population in some senses in sort of stasis with respect to its size. But is that sort of population that's remaining the same size, how is that different from what we had already? After all, if the population is not growing and shrinking, what's the point of adding births and deaths? Yeah, susceptible is still coming in. There's still population turnover, right? The population is still, it's a different set of people now than it will be 5 years from now, or 5 years from then, that are being exposed to infection. Some of them may stay all through the process, but some are turning over. So that was item one, and we're going to spend some time looking specifically at that. The second item I asked you to look at was the impact of adding a vaccination, representation of vaccination. And initially, I suggested just having the population divided between the susceptible, so there'd be a vaccination stock, and some people would start initially in that stock. And that works fine if you have a situation of a closed population. But if you have an open population, a population of people coming in and leaving, we're going to start to see that we want to have people get vaccinated over time. Because it's not merely some cohort of people, some same set of people that remain all through the simulation. We'll have people coming in and leaving, and we want the vaccination stock to reflect that. Okay? So initially I suggested you just sort of start people in there. So I, like you, built up this sort of model in AnyLogic, and I asked you to do it. Who can tell me, did people encounter problems doing this? What sort of problems did you encounter? Okay, no one wants to come forward? Well, I didn't encounter any problems either. Well, no, actually, I did encounter an occasional issue. One problem I encountered actually related to the question raised by, I think it was Kyle at the back there, with respect to, I put in a vaccination stock and divided people between it, and I noted that I started 80% of the people vaccinated, and I kind of calculated that number because I would expect it to achieve herd immunity, and the disease still took off. I said, what the heck? And guess what I had forgotten to do? What's really important, suppose you have a vaccination, a set of people who are vaccinated, and you now have, a lot of people vaccinated, but there's no flow between them. They just start vaccinated. How do those vaccinated people, how does the presence of vaccinated people affect the others? Why does it matter? Where's the coupling?
You didn't put them in the denominator?
Yeah, exactly. I didn't put them in the denominator. There needs to be that representation in the in the denominator that those folks are in there. So this is the Eclipse framework, so we can just click on the tab. So here's my little model. No, okay, the size of the vaccinated stock is not a representation of anything of great significance. It's a representation that I wanted but tried in prettifying it in some way. But here I had originally forgotten to add the vaccinated people into this total population. And that makes the world of difference. Why does it make the world of difference? Why does it matter that they're in the total population?
Population affects the
Prevalence of infection.
Course of infection.
Thank you. And that's actually true, but through the shadow variable here, it's kind of obscured here. So I'm going to, I find that disturbing that that's kind of hidden. There's a link between total population and it's kind of hidden because I had a shadow variable because total population used to be down here. So I'm gonna get rid of this shadow variable, and I'm going to here I'll to save myself needing to go to the palette, I'll just get rid of this, and then I'll take this guy here and bring him down. Hey, there we go. Okay, now we're cooking with gas. So now we see that the prevalence of infection depends on the total population. So if you have lots of people in the vaccinated stock, it means that the prevalence of infection in the population is, the larger the number of people who are vaccinated, the what of the prevalence of infection? The smaller prevalence of infection will tend to be for the same number of infectious people. And that makes all the difference when it comes to the force of infection. Because now each infective is going to be surrounded by more and more people they can't infect, right? Mm-hmm. Or conversely, each susceptible is going to be surrounded by more and more people that cannot infect them. So it really matters that that this prevalence of infection is affected by total population. So there's a lot of ways we could prettify this. I'm going to move that down there so the connections seem a little bit clearer. But there we go. Okay, so that was one component I added in, was this vaccinated stock. A second component that I added in was these elements associated with population turnover. So I had mortality rates going out of infective, susceptible, recovered, and births coming in. So perhaps you folks can tell me. Let's suppose we were to take a given one of those mortality flows without privileging it. Suppose we were to take this recovered mortality. How, ladies and gentlemen, what's the formula that you think I used for recovered mortality? If we scroll down here, what's the formula you think I used for recovered mortality there? Anyone?
Mortality rate times recovery.
Yeah, exactly. Mortality rate times recovery. Let me just make sure our remote guess can see what we do here. And similarly for infective susceptible. You could think of it as a first order delay sort of situation, although in a competing risk situation here, because it is also the chance of infection, for example. Okay, in births, the formula there. It's interesting, it's not, yes. Okay, birth rate times the total population, right? So there's a birth rate, 1% per year. The units of that are what? So the units of that would be, how would we measure? So what are the units by which? What's the yardstick associated with which we measure birth rate? It's what per what? The units are 1 over a year, where the 1 is an indication of something that's dimensionless. It's a fraction. So if we, or the chance, you could think of it, the probability, and those quantities are dimensionless. If we ask, what's the chance of getting heads in coin flips? Take a number of coins that we flip divided by, the number that are heads of coins that we flip divided by the total number of coins that we flip. It's coins divided by coins, so it's dimensionless. We could count in thousands of coins that are heads versus thousands of coins that we flip and divide the two and we'll get a fraction. So the unit associated with birth rate, for example, could be 1 over a year. We multiply by something whose unit, total population, whose unit is person, and we get something that's person over a year. And that's a flow, right? That's a flow into this stuff. Okay, so we have a dimensionally consistent thing there, and then this mortality rate is also 1 over a year, chance per year, right? It's a chance per unit time, and it's multiplied by susceptible to get a flow out of susceptible. So it's unit-wise, it makes sense. This is persons per year leaving here. Okay, this is the sanity check. Great, and in fact, AnyLogic and Benson, at least the professional version of Benson, will do unit checks for you. So you can ask it, kind of go figure, it will go off and check this. Great. So this is my incorporation of those elements. Did anyone want to ask questions about this?
What is the population turnover rate?
Oh, okay. Yeah, so this is a great question. And this is part of my my hidden agenda today, is to start introducing some familiarity with AnyLogic. So this little thing that looks like a slice of pie, what is that? Sorry? It's a parameter. It's a parameter. And what that allows us, basically a parameter is going to serve 2 functions in AnyLogic, okay? It's going to serve as a way of communicating assumptions, and it's going to serve as a place to hold values. So it's hold those assumptions. It's kind of a variable that holds assumptions. And by virtue of declaring it here, this is not something I would have expected you to know. By virtue of declaring it there, it's going to mean that when we have experiments involving this model, in the experiment, we get to specify it. Okay? So you'll notice there are some things that I've specified here that are constants, but I haven't made parameters. An example would be the contacts per unit time. I could have made it a parameter. I just didn't think it was something we want to focus on so much. I want to change it in experiments. But this population turnover rate, that's something I want to be able to specify for this experiment. I want it to be this thing. For this other experiment, I want it to be something else. So I actually, in some sense, privileged it as a parameter here, and it functions just like a constant, but it's one which we can specify when we create a new experiment in AnyLogic. Does that help? Okay, and we're going to see that we're going to be using those in spades in coming week. So and you may wonder, why did I do that? Well, this is me as a software engineer, and the fact is, I knew that we might want to, in fact, even in front of you, we might want to change the mortality rate to be different from the birth rate. And I didn't want to just have these guys depend directly on a thing called population. I wanted the two to be the same initially, to be so the population is in stasis in terms of its size. But I didn't want them to directly depend on, like susceptible mortality to depend on this population turnover rate, because if we want to separate them in the future, we'd have to go change all these different equations, the equation here, the equation here, the equation here. And I didn't want to do that, especially in front of the class, and especially burning class time. So I thought, rather than doing that, as I am wont, I'm going to abstract it. And so we have a mortality rate, and these guys depend on the mortality rate, and this guy depends on a birth rate, but each of those depends on the population turnover rate. And so if in the future I want to have a separate thing, I could delete this, boom. And now those two could vary independently, but for now they're both going to be set to the population turnover rate. If in the future I want to separate them, I don't have to change an equation. I just separate them out. All I have to do is specify a separate mortality rate and birth rate, and I'm done. I don't have to go change the equations across the model, remember where it's used or anything like that. Does that make sense? Okay. Other questions? I put in something here I didn't explicitly ask you to do, but I put it in with malice of forethought. I put in a vaccination process here, so that people could get vaccinated over time, where the default value associated with it, as specified by this annual vaccination rate, is 0 by default, but we'll see why we might incorporate that later. So ladies and gentlemen, we have this vaccinated stock, and the initial value of this vaccinated stock is indicated by some initial total population, or initial uninfected population, times some initial fraction vaccinated. Okay, initial fraction of that population vaccinated. And you could see that's its initial value here, because stocks we have to specify initial value. Yeah?
I was wondering what the difference between the dotted lines and the sum.
Dotted lines it means it depends on it as an initial value. Whereas if it depended on it in its formula, for example, this thing here depends on vaccination, this vaccination inflow, well then it's an inflow to it. Here it's a dotted line because it's an initial value. Okay, that's one way to interpret it. That's where it depends on it. Okay, so it's not a flow into it for sure because it just specifies its initial value. Okay, questions? Okay, so ladies and gentlemen, what's the impact of this? Let's first confine it. Let's divide our difficulties. These are nonlinear models, but with nonlinear models, it's all the more important because the behavior can be unexpected. It's all the more important to experiment with them in a step-by-step fashion, bit by bit by bit, adding components in and developing that intuition for what's going on. Because when you run the whole thing, it won't be obvious what's contributing what, because it's a mixture of a bunch of different things interacting. So it's important to add things in one by one. So with that philosophy in mind, ladies and gentlemen, I would like to first suggest we examine a situation where we have no vaccination, and we're in fact I'm going to remind us of what we saw last time. So I'm going to run this, a new experiment here, and it's going to be no vaccination, closed population, 0 population, okay? So what should the parameter values be for this? Population turnover rate would be 0, no vaccination, initial fraction vaccinated 0. So as it turns out, the default. So ladies and gentlemen, what should I see?
Standard SIR
Okay, good. I'm going to show you a little bit about AnyLogic and doing this, again, with malice of forethought. So one thing I want to do is I want to have a nice graph. And I created this already, but I'm going to just destroy it because I want to show you how you create it so that you folks, too, could do this. Okay, so AnyLogic, unlike Vensim, does not have notions of runs that you can just load and the currently loaded runs. Instead, if we want to show a graph here, we can do so on an ad hoc basis by clicking on a stock. I'll show you that. So here's our thing. We'll run it. Right-click on it to run. Right. Let's do that again. We've done it before, but just to remind people, run by right-clicking on it. Right. Here we go. Here we're running it out. Let's tell it to go as fast as it can. Boom. Okay, and I want to see what happens. I can click here, and I can tell it, go show me a graph of what you've been doing. But it only shows it for a recent period of time. It doesn't show me it's a little bit restrictive. Sometimes it's very useful, but it's restrictive. So I'm going to instead add a time plot in. I'm going to add a plot that will plot out the value of one or more variables over time. So here I'm going to add a time plot, and I'm going to tell it, okay, go and plot out a few of the state variables. So I'll call it time plot stocks, okay? And we're going to add a data item. And what data item is it going to be? It's going to be susceptible. Hey, come on. Because it won't do it while we're projecting our screen. Okay, so I'm going to add another one. I'm going to do infective, right? I'm just trusting I'm remembering those names right. I can go over here and check. Okay, yeah, there are the nice names. Okay, and so I need to get back to this. Fine. And then I want to do recovered. Recovered here. Yes, recovered it's called. Okay, good. Not recovereds. Recovered. Okay, great. So that's all well and good, but if I did that naively, something unfortunate would happen. What will happen? Can anyone tell me? I'm going to do it in front of you, and we'll see. Well, it's almost like a snake chasing its tail. There we go. See, it's just scrolling on. It occluded the area of interest. So I don't want that to happen. So I'm going to go, and I'm going to frob this so that the time window is of length, I think I told it to be of length 500, but basically anything that's that or above, and I want it to display up to 100 time steps. It's set to update automatically every one time step, and I want it to display up to 100 of the most, 1,000 of the most recent time steps. Okay, great. So I just added that time plot. I'm going to run it. You folks are welcome to follow along, and here we go. Let's run this out. No vaccination, closed population. Here we go. So what are we seeing there? Can anyone rehearse for me the narrative that I hope is now written in your minds clearly? What's going on here? Okay. Okay. Good. Good. So susceptibles are going down in a monotonic way. Why monotonic? Why aren't they leaping around? Okay, it is a first order delay. Well, actually, it's not technically a first order delay because it exhibits a changing rate constant. Your chance of leaving per unit time if you're given susceptible is going to be changing over time. Why?
Because it depends on the number of susceptibles and the number of
infectives. And so, yeah, if there's a lot of infectives, your chance is going to be higher than now. So it's not a classic first order delay with a fixed constant, but it's with a varying constant. Okay, so it's decreasing because of that. But what's the more fundamental reason it's decreasing? There's no inflow. No inflow. It's got to decrease. Well, of course, stay the same, right? Okay, so that's decreasing. And recovered's by the same notion is going up. It has no outflow, right? It can only stay the same or go up. I mean, it's going up to a high level. The most interesting one, of course, is infectives. There we go. Control mouse wheel. We'll zoom in like that. So what's going on with infectives? Again, can anyone give me the story? What's going on early on with them? What's going on in kind of this region? What's the story there? Exponential increase because rising prevalence of infection. Lots of susceptibles around. Beautiful. Beautiful. The fire can grow very quickly because there's lots and lots of things going on, right? I hear a little, great. So you could think of it as each infective there will replace themselves by a certain larger number of infectives before they recover, right? So maybe one infective becomes two by the time they recover. So in other words, they've replaced themselves with two infectives. And then each of those replaces themselves with two more recovereds because there's so many susceptibles around that, really they're not yet inefficient because of in terms of transmitting. They've just plenty of people to infect. So each of them replaced by two. It goes from 1 to 2 to 4 to 8 to 16. And so it rises exponentially like that. They're replacing themselves by what's called the basic reproductive number of people. And that's the number of people they infect in the course of their illness within the confines of a totally susceptible population. Each of that infective will replace the basic reproductive R0, R0, depending on which side of the Atlantic you're on. R0, the basic reproductive constant, okay? So each of them is replacing themselves by that many people. Of course, this applies, as we've argued, not just infectious disease, but in, each new iPhone user, iPhone 5 user infects two others, and so it goes from one person in Saskatoon to 2 to 4 to 8, and so on. But some of us, ladies and gentlemen, have been infected by a different strain. In any case, okay, so that's what's going early on. What happens at this peak? What's going on there? What's the narrative there? This will be important for understanding what we see different with the open population in a minute. What's going on at that peak?
R0 is 1.
R0 is 1. Beautiful. The individual level, each infective infects one person. They replace themselves by just a stand-in, when they recover, and so it's not going up or down, right? It's no longer rising and falling. What else is true there? The distinguishing feature when it's reached its peak. It's no longer increasing, no longer decreasing. This is the value of the stock, and therefore what must be true? Inflow equals outflow. The number of, what are the inflows, what are the outflows? We're graphing out in red here the number of infectives, and therefore inflow is new infections. So the number of people getting sick per unit time is equal to the number of people recovering per unit time. So at a population level, that's what's distinguishing there. Oh, those are testable things. Okay, now what's going on? Why is this decreasing so quickly after that? Give me two reasons that the number of infectives is decreasing very quickly.
The exact opposite to why it was decreasing.
Not just that. Yes, that, but
Susceptible people, and you're also the prevalence of infection is going down.
good. So we've got two things working against the number of infectives. We've got lots of infectives to recover. And we have fewer and fewer susceptibles now. And that drives down the number of infectives, which further means that we have fewer infections, and therefore the outflow, number of recoveries, is even larger than the number of new infections. And so we get this kind of virtuous cycle, as it were, where the number of infectives is dropping very quickly for both those reasons. And it drops down and people are recovering, and then it goes down to low levels. Now, ladies and gentlemen, at the end of all this, if we look out far enough, are there lots of infectives that still remain? Why not?
They've all recovered.
They've recovered, and if one were to come in, they'd be surrounded by lots of people who can't get the bug because they've either already got it or, well, okay, they're no longer sick. So, but they're so inefficient transmitting, it's going to blip out. Maybe they'll affect one person then before they recover, but that person will probably infect less than one, and it just goes down. The effective reproductive number, the number of people they will infect right now, is less than one before they recover. The number of people they'll infect right now, over the course of their illness is less than one. But the reason I said right now is I want to distinguish it from the basic reproductive constant, which is in the very specific case of a totally susceptible population. So other than that, infective, everyone else is susceptible. That's when you talk about the basic reproductive number. How many people in that worst of all cases, where you've got that infective in a population that's otherwise totally susceptible, how many do they infect? Effective reproductive number says right now, in whatever situation we're in, however many susceptibles there are right now, how many people is an infective infecting before they recover? That's the effective reproductive number. We write it R star, the effective reproductive number, okay? And that's a different story. And as was mentioned earlier, where does that cross 1? Where does that cross below 1 or 2-1? It crosses at the very peak. That's when it peaks. And after that, it's all less than 1. It's all downhill from there. And so the disease is not able to persist. And ladies and gentlemen, it basically goes until extinction. I mean, we're dealing with continuous numbers, so it just goes arbitrarily low. But what does not go to extinction, ladies and gentlemen? Number of susceptibles. And I argue that that's kind of like fire, wood in the fireplace that always remains unburned. There's always going to be some those people that escaped infection. Okay, that's great. So we looked at this last time. So, ladies and gentlemen, how does having an open population infect things? How does it affect things? Okay, so I'd like to challenge people here. Good. There's loops. Yes, there are loops. There's loops associated with oscillations. So I'd like to suggest no vaccination, and we're going to have a 1% turnover of the population. 1% per year. Okay, so now we've got the situation where people are coming in, just in this one we've been looking at, no one's been coming in for births, no one's been leaving, no one's been vaccinated. We've just got these, and they're going down like that, and eventually people end up, by and large, here with some residual. Now we've got births coming in and deaths going out, but in balance for the total population. So now, ladies and gentlemen, we have, what's the key feature we have now that's different? We have new susceptibles. It's like wood is being added to the fire. Okay, so we've run this out, and, okay, sorry. Yes, okay, thank you. So let's go. Okay, there we go. Great. So I thought, so I think the parameters are not set properly. Thank you. That didn't seem right. Population turnover rate, 1%. Vaccination, both those are 0. Thank you. Thank you very much for catching up. Much appreciated. Okay, there we go. That's what we got. What is going on? First of all, let me make it so it only displays till, because it's kind of distracting. It's only displaying for half that time. So I'll go down there and frop that. So let's go have it display only time window of 500. I thought it would be fine, but it's just too distracting. Okay, we may expand that later. Good. Okay, so what's going on there? Why do we see cycles?
guess as recovered people leave, it reduces that sort of herd mentality or herd immunity thing you're talking about.
Okay. Yeah.
The infectives aren't surrounded by enough susceptibles.
And who's coming in to replace those recovereds?
Yeah, more susceptible.
More susceptibles. So, ladies and gentlemen, we see what in essence is, what does this look like? If you sort of squint at it and use your imagination, this looks it looks like a what?
Sinusoid is an exponential decay.
Okay, yes, it does look like that. And that suggests that it's not so different from this thing here in some respects. So it's like a secondary outbreak that's occurred here. It's like a minor secondary outbreak. The blue, what is that representing? Susceptibles. Now, they are no longer monotonically decreasing. Why not? Because there's inflow now, right? And you'll notice what lays the groundwork for the secondary outbreak is a what in susceptibles? An increase in susceptibles. It rebounds to a level that is unsustainable. Well, that is more than enough to trigger the infection. The endemic level of infection, ladies and gentlemen, I will repeat this later. The endemic level of infection, at this endemic level where it stays persistence in the population, we are in a state of balance. We're in a situation where the stock is no longer changing, which tells us what? That the in equals the outflow. And at an individual level, how many people is each infective going to be infecting at that equilibrium? One person. One person. So it's going to that level, but you'll notice there's a level of, this is the level of susceptibles which is required to maintain that, right? That's the level. And earlier on, that level of susceptibles was exceeded here. When that level of susceptibles goes above that endemic level, it tells you that the number of people, the R star, the number of people infected by infective before they recover can now be greater than 1. So that's why you get that secondary outbreak. So the number of susceptibles rebounding like this, rebounding, paves the groundwork for a subsequent secondary outbreak. Okay. I'm going to come back and emphasize these points, but is that starting to sink in? Okay. Let's take a look at a slower situation where we have a very small level. Well, no, let's go look at a heavy level of turnover. There's lots of turnover in the population. What do we expect to see there?
Higher endemic problem.
Okay. So, I probably did it again. Let's go try that again. Okay, here 10%. Gosh, I don't know. Okay, 10% turnover. So 10% turnover per year. Each person will remain in that population for how long before leaving, on average? If you have a 10% chance per year and for leaving, you stay there on average?
10 years.
10 years. Thank you. Excellent. Excellent. So here, what's going on?
The endemic level of infection is much higher.
Much higher. Much higher. We get a situation where it quickly establishes this sort of equilibrium where the number of susceptibles is small, the number of infectives is actually quite large here, and we get a situation where essentially the outbreak sort of goes up and then it comes down at this modest level. Now I'm checking. Yes, and you'll notice here we have a situation. Okay, that's interesting. I'm going to have to think about that. So here we have mortality here. Okay, these are about 60, 60, 40, and births is 100, which is interesting because wait, this is 40, yeah, 40, 60, 60, okay. So why are those totaling up to something different than bursts, which is 100? Okay, that's not fully computing here with me. I'm going to have to go, okay, I must be missing something here, but I have set it so the total population should be in balance. So let's go look at the total population. Let's go check that out over time. It's in balance at 1601. Okay, so how is it that we have this many leaving per year, 160?
Because it's depending on the value of the stock, not on the total population for those mortality issues.
Yeah, it's just that this is the equilibrium value. I must be missing something very obvious here, and
Maybe the population wasn't in equilibrium at the start.
yeah, it's possible. It's just normally you'd expect inflow equal outflow for the whole population as well. It's certainly inflow equals outflow for each of these stocks in isolation, but I would have expected bursts to equal deaths for the population as a whole, for it to be in balance like that. Okay, I need to think that through. It's a little bit aside, but I was wondering why those two go up to both to be 600. Okay, we'll probably come back to that. Let's go look at a situation where we have an extremely slow turnover. What do you expect to see from that? A turnover rate that's, let's say, I'm going to say 0.25%. What would you expect to see?
Perhaps no endemic infection.
Okay. So parse for me what's going on here.
Multiple secondary outbreaks.
Okay. Yeah, so what we've got is we've got an initial infection, and it's almost as if the rate of turnover in the population is so small it's you could be excused for looking at the number of infectives by thinking this is a closed population, if you looked at them alone. What's happening, however, is that this is building up. And it's building up to a level that's above the endemic level, above the level that's sustainable. But you notice that this number of infectives is going along. This is building up, building up, building up. Why isn't that number of infectives just immediately following it up? That's the question I want you to ponder. Sorry? So ideas that there's sort of an inertia associated with recovered. Others?
Tipping point, the number of contacts the susceptibles have level.
Okay. So it needs to go up to a tipping point. It needs to go up to a point where you cross that critical threshold where each infective is affecting more than one susceptible. Yes, that's a component of it. Let's talk about this issue in a little bit more detail. So now we're introducing bursts and deaths. The question is, how does it change long-term behavior? Under what conditions would the stock of susceptibles still be declining, and stock of infectives still be declining? So now we have this situation like we had last time, but we have these death flows and a birth flow here. This is the total population here, and we just have some alpha. But here, alpha equals omega. Okay? Okay, we'll come back to that. So here's with bursts and deaths. This is the sort of components we have. Now, a key feature of this is delays. The fact that this, ladies and gentlemen, oscillates around and doesn't go immediately to a new equilibrium. The fact that in engineering terms, you talk about an underdamped system. So it's exhibiting these oscillations before settling immediately in a new equilibrium. That's an indication, ladies and gentlemen, of delays. The occurrence of significant delays. And I'd like to talk about these delays. For a while after infectives start declining, okay? For a while after they've been going down here, they're still and this is occurring while susceptibles are below the endemic level, they still deplete susceptibles enough to really deplete them down to a low level. You'll notice that, and maybe I'll show it on the screen here in this pronounced way because it's actually probably clearer when I depict it in the big screen here. You'll notice this is the point where infection is no longer can't sustain this infection, where it's we have more recoveries occurring. Recoveries are occurring faster than new infections, where each infective now infects on the downslope less than one new infective. They're not even replacing themselves with a new infective when they recover. It's all over for the infection, you would think, but there's a delay here. The number of susceptibles is still dropping. You notice that after this peak is occurring like right about here somewhere. And yet the number of susceptibles is declining still. Why? Under what conditions would the number of susceptibles still decline? Why does it continue down? Why doesn't it just stop going down? Under what conditions would the stock of susceptibles still decline? If the inflow is less than the outflow. And what, ladies and gentlemen, in this model, what is the inflow, what is the outflow for the number of susceptibles, in the population? Okay, yeah, the rate of births. If the rate of births is less than the rate of infections, even if it's not sustainable, it's going to drag down the number of susceptibles. So, ladies and gentlemen, there's going to be a delay between when this infection is starting to die out and when it's having a very material impact on the number of susceptibles. So it's going to drag the number of susceptibles down to a level that itself is unsustainable. Unsustainable in the sense that it's not going to persist because the number of births is going to be coming in and pushing it. But so for a while there's this delay. Remember I said stocks are associated with delays. They're associated with inertia. The fact that we have the stock of infectives that it has to drain means that it takes a while for it to drain. In the meantime, they're going to be depleting the number of susceptibles below this sustainable level. Does that make sense? Below this level at which the system is all in balance. The system is in balance at the level where the number of susceptibles is equal to this. That's when it's going to be in balance. But it rates it well below that. And then that's going to set the ground. That's going to set the stage for another long delay. For a while, susceptibles are going to be rising. They're going to be rising up to that value where it's sustainable for the infection to spread. They're going to be, and it's going to take them a while to get to that level because they've been so depleted so much by that period of high infectives. And during all that time, where the susceptibles are still rising up to that sustainable level that will sustain R star, the effective reproductive number equals 1, will sustain each infective to replace themselves with at least one infective. Well, it's still not yet at, the number of susceptibles is still not at that point. What's going to be going on? It's rising up towards it, but what's going to be going on to the number of infectives then? It's going to be depleting. It's going to be depleting. So, ladies and gentlemen, there's a mutuality here. There's a feedback here that's central. So, look, initially, the number of infectives is going to be going from 1 to 2 to 4 to 8, etc. And it's going to drain down the number of susceptibles. And this is going to build up a big head of steam, a big sort of value for the stock of infectives, right? And the stock of infectives, at some point, it's going to get so few susceptibles around, it's not going to be sustainable anymore. They're going to replace themselves with just one person, and then increasingly with less than one person. But as long as they are sizable in number, and it's going to take that stock of infectives a while to drain, they're going to be depleting susceptibles further, right? And susceptibles is going to be depleted further past, way below this level where it's sustainable, where it could sustain the infection. And all during that time, as the number of susceptibles is draining, it's going below its value, its sustainable value. So it's going to take it a while to recover. It's going to recover eventually through bursts, but that's going to take a while to fill it in. And all during that time where now susceptibles is below its sustainable level, that's going to mean that, by definition, the number of infectives is going to go down. It's not sustainable. Each infective, they're going to recover less, they're going to infect less than one person before they recover. So the number of infectives will be going down. So ladies and gentlemen, this stock and flow dynamic, the number of infectives is drawing down here, but meanwhile it's dragging the number of susceptibles down. The number of susceptibles is going to start to recover, but as long as it's below this sustainable level of somewhere around 200, all during that time, the number of infectives is going to be depleted. And it is going to then eventually start to recover once the number of susceptibles rises to the point where each infective is surrounded by enough susceptibles to at least replace them with one person. And that fact that it takes time for the number of infectives to recover means the number of susceptibles can go higher yet. The number of susceptibles can go higher yet because the number of infectives is not yet at a point where infections, exceed bursts. So susceptibles is going yet higher. So infectives will still be rising for a while, even after infectives start rising, because the bursts are greater than the number of infectives. So these susceptibles are going to rise to a level that's well above the level needed to sustain the infection. And finally, of course, that leads to the number of infectives to peak here, to peak up at this point and cause a secondary outbreak. Yes?
In the graph,
yes.
Is there a reason why the number of infectives didn't go down to zero? Because it looks like it's so close to zero for so long.
Yes, there is a reason, and we'll get to that in a minute. Can I thanks for the question. It's a great question, and we'll talk about that shortly. Let's try it even at half that level, the 0.5% turnover. What do you think will happen now?
Dampening will get stronger.
Okay, we don't even see it now, but that's just because of artificial occlusion. What would we need to do? Well, first of all, we need to run it out further. So I'll go and do that. Where is it? 0.5%. I'm going to run this out further. I'm going to go to the model time of the experiment, and I'm going to run it out to time 2000. And I'm going to set this nice graph so that it keeps up to 2000 data points and shows me all 2000. Okay, there we go. Okay, great. So we're going to run this, and what do you think we'll see? More pronounced secondary outbreaks yet. Again, very slow accumulation of new susceptibles due to bursts is going to allow, get this, mark my words, very slow accumulation of new susceptibles through bursts is going to mean infectives decline and decline and decline and decline and decline and keep on declining for quite some time before the number of susceptibles gets back to a sustainable level. Does that make sense? It's going to take a long time for the number of susceptibles to occur. The number of susceptibles got really hammered by the number of infections in this region here. It got really, really low because all during this time, the number of infectives was declining, but it was still, it still had that inertia. It was still draining the number of infectives. Draining the number of susceptibles because bursts are so low, right? Because bursts are so low, the number of susceptibles went way, way, way down, because even as the number of infectives came down, it was still causing more outflow than inflow. It was still causing more infections than births. So it went down to a very low level, and now it's going to take a long time to recover, a very long time. And all during that time it's going up to the sustainable level, the number of susceptibles is draining. So it gets to a very, very low level. This number of susceptibles now reaches this sustainable threshold and rises, but it takes a while for the number of infectives to now get back up to this level where it's sustainable. And then you have this secondary outbreak, and it draws down the number of susceptibles dramatically. And then you have another secondary outbreak and another outbreak. But ladies and gentlemen, inevitably, this is being drawn towards what here? It's being drawn towards equilibrium. You see the fox is showing its tail at the end here. We're being drawn towards this equilibrium. And indeed, that's the character of these situations. We get these secondary outbreaks, but they're damped. They're damped, and over time they go towards some equilibrium. We'll see a different situation when it comes to percolation and agent-based model shortly. But here they go towards a point which is in equilibrium. And at that equilibrium, state to me, the system is in balance. All the stocks are in balance. And therefore, what must equal what? Let us count the ways. Let you count the ways. So please, if this system is in equilibrium, every stock up here is in this sort of exquisite balance. What must be the case for the system as a whole to be in endemic equilibrium? Ignore the vaccinated for now, but if all these stocks are in balance and we have deaths and births but no vaccination, specify for me things that have to be equal. Births equals to deaths. Okay, good. Another?
Births equals infection.
Births equals the rate of births, number of births per year is equal to the number of infections per year. How about another thing?
Plus susceptible mortality.
Oh, yeah, plus, thank you. Plus susceptible mortality, that's exactly right. Okay, good. And how about for infectives?
Infection equals recovery
Plus infection mortality. And for recovered, the number of people recovering equals the number of people dying from that stock, right? Or I shouldn't say always dying. This says mortality, but it could be a removal of other processes. We could be focusing our attention here on children of 0 to 10 years of age, and they could simply move on to an older age category where basically everyone is recovered, and so we consider them outside the scope, and these children mostly mix with each other. We represent those situations with these models too. So it's not always true mortality, but it's removal through one process or another. So here we're going towards a situation of equilibrium. And ladies and gentlemen, we call that sort of equilibrium an endemic equilibrium. Okay? We call it a situation of stasis endemically. And at an individual level, we've just enumerated the situation for stocks, and that's good. At an individual level, what does this mean about the number of infections a given infected will have over the course of their illness?
So R naught is 1.
R star is 1. R naught is the situation if they were surrounded purely by susceptibles, which is a very different story. R star, the effective reproductive number, is 1. They're infected one person before they recover or die. Yeah. So that's the sort of hallmark of this situation of endemic equilibrium. So this peak, point where rate of new infections equals rate of recoveries. Each person on average affects one person before recovering. Level of susceptibles at the lowest level where the infection is sustainable in the short run. It's at that level which allows me to infect at least one person before I recover, right? And at this point, the number of susceptibles and the number of equals the number of susceptibles at equilibrium. You look over here, and it's the same point as here, and it's no coincidence. The blue I'm talking about. It's no coincidence. That is the point where r star equals 1. And that is why there's a peak there. That's why there's that peak. We talked about why is the number of susceptibles rising to well above its sustainable level. Well, it's rising because it takes a while for the number of infectives to sort of recover from their very, very low levels. Why is the number of susceptibles still declining well below its sustainable level? Because the number of infections is still greater than the number of births, the rate of births, because the number of infectives is still quite high. There's inertia in the system. It takes a while for the number of infectives to be drawn down. And the net fraction of susceptibles at endemic equilibrium is the minimal sustainable value of susceptibles. It's the value where the properties hold. Above this level, yeah, let's talk about that. Ladies and gentlemen, so suppose, let's do a Gedanken experiment. A simple thought experiment. Okay, so we have these susceptibles here. What would happen if I nudge upwards the number of susceptibles? I have extra susceptibles come in by the busload into Saskatoon. What will happen? Okay. So those new susceptibles will bring new opportunities for infection. It will surround each endemic infective circulating in Saskatoon by more susceptibles. It'll be able to spread a little bit, and it will bring the fraction of susceptibles back down to that original level. If the number of susceptibles leave, and there's now too small a fraction of susceptibles, then what will happen? Force of infection goes down, the number of new infections goes down, and therefore there's fewer infectives around, and therefore the system gets back into balance, back into a situation where the fraction of susceptibles is back at its comfort zone. So, there's a negative feedback pulling it back to this situation. If you nudge it upwards, it pushes back against it. If you nudge it downwards, it pushes back against that influence. It's being drawn back to this point. We talked about the basic delays here, and I'll put this slide up here. We don't have time to go over it yet again, but it's worth realizing that delays are what allow this disequilibria to occur. The fact that there's delays in this, delays associated with draining the stock of infections, delays associated with replenishing the stock of susceptibles. Those delays are what allow these disequilibria to persist. And what allows these swings to occur. Without those delays, ladies and gentlemen, it'll quickly come to a new equilibrium. We overdamped, boom, acquire a new equilibrium. The fact that, do you remember this occurred when we had very low rates of immigration? That's what allowed it to go down to this very low level and to build up slowly, and that's what allowed that equilibrium to occur. If we had very high rates of turnover, we get a situation where the delays are far less. So if we have, for example, 10% turnover here, we'll go to parameters here, make sure it's 10%. Each person stays in there approximately 10 years. And we get a situation where it's gone to its equilibrium almost immediately. It's going very, very quickly at that rate. Okay, so we have these delays. We could depict this sort of situation in a phase plot or a state space plot. So here we have number infected on the vertical axis, and I apologize, the number of susceptibles. The title of the slide down there is somehow, or this axis is somehow off. It says susceptibles. You could see the top of the S peeking out. So here we have a number of susceptibles. Can anyone tell me, okay, if this is number of infectives and this is number of susceptibles, what's going on here? Can someone give me a narrative, a story associated with this? What's happening?
Susceptibles decrease and infectives keep on rising.
Good. Good. Susceptibles decrease and infectives rise, and you get that replacement. This is why it's almost at a 45-degree line. Each susceptible is replaced by an infective almost exactly early on, and then it's no longer at 45 degrees. It's sort of shooting along here. It doesn't show you exactly what time, but these arrows show the direction it would go. If you put the state in this system, it would show it where it will go. So initially we have very few infectives, like 1, and many susceptibles, and then it starts rising up here. And then it becomes not straight, but curvilinear. Why? What's going on? Why is there no longer a direct, for each susceptible decrease, the effectives increase by that amount? Because what's occurring? Well,
Each infected is not surrounded by enough susceptibles to keep passing it on at the same rate.
well, that's true, but there's also, the reason there's not a one-to-one, there's no conservation of people between susceptible and infectives because there's another stock, recovereds. And hence it isn't sort of a one-to-one trade-off. You're absolutely right, though, that's why it's getting slower, that it's not just going like gangbusters up through the other axis. It's getting slower, and then you get the situation where, now the number of infectives is decreasing, the number of susceptibles is decreasing. What's got to be increasing? Recovereds. Okay, so then we go down and we get into the situation where, boom, we're now in a situation, this is no birth and death, no births, no deaths coming in. We're in a situation where we have very few susceptibles, few infectives, 0 infectives, and lots of recovereds.
Question.
Yes?
Is it right to think of these graphs as if you were to put an initial point anywhere on the graph,
Yes.
factors would indicate sort of your path where
Precisely.
you go from that?
Precisely. So this is summarizing in contrast to these sort of graphs, which show one run, one scenario, one situation. These show basically gives you a sense of what would go on under all sorts of scenarios. So if we started here with a population, that was, say here, a population that has 200 infectives and about 700 susceptibles, we'd expect it to kind of go in a situation like that. So these are called phase plots. Now this is with a high birth and death rate. And now we're being sucked in a stable way to the vortex of endemic equilibrium. Just like that. It's coming up and sucking it into this state. And you'll notice that there's this almost a limit cycle around here. It's exhibiting this sort of whirlpool-like behavior, and that's associated with what? The fact that this is curved around like that is associated with
Equilibrium.
it's going towards an equilibrium, and it's sort of focusing in on this point, and the fact that we go up to this point, and then we come down to it, and then again we're at the same number of susceptibles. It's oscillations. So this is a high birth and death rate, modest birth to death rate, very smaller yet. Here we're getting a situation where very small birth and death rate allows the number of susceptibles to be drawn very, very low before it regroups and starts to recover again. It's what allows it to take a long time to recharge as well. So these are illustrations of how the phase plots change the state space. This is a depiction of what we call state space of a system. Each point here on this diagram indicates a situation where the system is at a specific point. But what I mean is that it's a specific susceptibles, number of infectives, and number of recovereds. And we could imagine, as was said earlier, starting the system at a certain point, and then it just follows the natural currents. These are kind of the currents of the system, the natural currents imposed by those equations, those formulas in the model. So imposed by these formulas that are behind there. And that's what allows it to go in. And so this allows us to kind of generalize what would happen under all sorts of different particular scenarios. And we can see the effect of parameter values in changing it. And you can see what a tremendous impact, ladies and gentlemen, we have going from a situation of a closed population to an open population with population turnover and with lower and lower rates associated with population turnover. So how many equilibria do we have? Well, we talk about an equilibrium. We saw it today. An equilibrium is a situation where what? We speak about a fixed, we call it also a fixed one. It's a situation where what is the case? Where the system is in, it's a state of balance. It's a stasis. And nothing, the stock values aren't going up and aren't going down. I'm glossing over one thing. There is a term dynamic equilibrium, which can have sort of a repetitive situation that recurs just ad nauseum forever. But here we're talking about a static equilibrium, a situation where it's in stasis, it's in balance. And ladies and gentlemen, when we have a situation like this in balance, when the stocks are no longer changing, what are the values of the left-hand sides here? 0. 0, 0, 0. There's no net rate of change of x. The number of susceptibles is constant. Not going up, not going down. The derivative of it over time is 0. Same thing with infected, same thing with recovered. And the beauty is, if we express it like that, we can actually solve for the values of SIR at which that occurs. It's a series of equations, either in closed form or numerically. We can actually solve and find the locations of those equilibria in terms of things like alpha, C, beta, mu, alpha, and omega here. We can solve for that. Is that clear? If not clear, is that plausible? Okay, so the key point here is that an equilibrium is defined by 0 here. And guess what, folks? There's more than one equilibrium typically. And in fact, it was a mathematician of great renown. How is it? I can't remember his name. He was called by one of my professors in undergraduate the best graduate student ever. Galois. How could I forget his name? Do you know how he perished? The impetuousness of youth. How a man can be so brilliant in one area, but so lacking wisdom in another. Does anyone know how Galois died? Does anyone know the circumstance of his death? No? Oh, man. So Galois has contributed to history, bequeathed to history, a set of his scribbles in a notebook that he wrote feverishly the night before he had scheduled a duel. And he had a premonition that he might die. And so he spent the night just writing down mathematical insights of various sorts that he had had. Closed the notebook, went off to the duel, he was killed. And as you can expect, it was over a certain young lady. And he died. He died. And so we have these notebooks from him that are filled with all these gems of insight. He was a graduate student at the time. So don't you get ideas, folks. Nor you undergrads. But Galois had contributed across a wide variety of different areas. And one of the things he proved is if you have more than 5 equations like this sort, you can't in general solve the quintic. So you can't always solve it in closed form. But you can solve for the location of these fixed points, these locations of these equilibria. And generally there's going to be several of them in a type of contagion model like this. One is a disease-free equilibrium, situation where there's no infectives, everyone is susceptible. Or vaccinated. Another one is an endemic equilibria, where it's a steady state equilibria. The infection stays resident in the population. And the idea is that children often get exposed when young. They acquire the infection, and it may be protective against reinfection, so they're essentially recovered. And it just stays like this over time. But in these sort of situations, we often don't get the sort of stability we see here. And we're going to explore why when we are looking next at agent-based models. The key thing is, often for people who build these models, can we make these equilibria stable? From a public health perspective, which of these equilibrium would you like to be stable? Would you like to attract a disease-free equilibrium? You'd like it so that it's stable in the sense that if someone were to come into Saskatoon with the condition of interest, with that pathogen, shedding pathogen, that there's no outbreak that occurs, right? No, it's resistant to it. In the same sense, ladies and gentlemen, that we have resistance at this endpoint here, that it just pushes back against it, and that it dies out quickly. It dies out immediately because that infective is surrounded by so many people who can't get it that it just dies out. And we want endemic equilibriums to be often unstable so that they go towards the disease-free equilibrium. But all too often what happens is disease-free equilibrium is unstable. Think about Ebola. And the endemic equilibrium is stable. So it pulls it in and it keeps it in that state. And that's the situation we've been seeing. But ladies and gentlemen, as a final point here, what happens for those who experimented? What happens if we introduce vaccination? So suppose we have no population turnover and we have vaccination occurring now. Sorry, what was that?
The peak is lower than for the infectives.
Yes.
Time point wise, it appears
Okay,
pretty
so we can get a situation where, in this case, it's 80% vaccinated. Well, maybe since time is really over here, I think I'll leave this for just the first opening minutes of next time. What happens when 80% in this model, we have a situation where we have contact rate of 10 people per unit time. Mean time until recovery is also 10, and we have a probability of transmission beta equal to 0.04, and then we start with 80% of the population vaccinated. I'd like to ask that, and then we can briefly look at how that interacts with an overall population. Okay. But for next time, I'm also going to ask you to try your hand at something different. I'm going to ask you to try your hand at following a little exercise, building up a simple agent-based model that's going to simulate infection spread. Okay? And we're going to compare some aspects of the behavior of these sorts of models in coming classes. Okay? Very good. So thanks very much.